Right, so section 9.2. I guess I could call it part A because I don't think we're going to finish all of it today. So section 9.2A, infinite series and geometric series. I don't know if I'm be able to write it all here, but there you go. Geometric series. Let me move it down. And there is going to be an nth term test for divergence at some point. Okay. We'll get to that when we need to. But let's do some definitions here. So an infinite series. Now, just so you know, the difference between a series and a sequence is that a sequence has a bunch of terms, okay? So like you could say the terms 1, 2, 3, 4, 5, 6, that's a sequence of numbers. A series of those numbers means you just add them together. So 1 plus 2 plus 3 plus 4 plus 5 plus 6. So the difference between a sequence and a series is that one is added together, the other one is not. Okay, so a sequence is just a bunch of terms. A series is the sum of that bunch of terms. Okay, so that's the difference between sequence and a series. So if A sub n is an infinite sequence, if it's an infinite sequence, then the sum as n goes from 1 to infinity of A sub n is equal to A sub 1 plus A sub 2 plus A sub 3 plus etc. plus A sub n plus etc. is called an infinite series. Now remember, we in section 9.1 we talked about how a sequence or an infinite sequence would be like A sub 1, A sub 2, A sub 3, etc., all the way up to A sub n and so on, right? So we would say that A sub 1 through A sub 2, A sub 3 would be called the terms, right? So we could say A sub 1, A sub 2, A sub 3, etc. are the terms of the series. Okay, now if you want to add these up, you don't have to always add up everything. You can add up some parts. So we call them partial sums. Okay, so let me put it right here. Partial sums so you're just adding up a certain amount of them, okay? So partial sum, they look like this. So S sub 1, big S sub 1, means just add the first term. Well, that's kind of ridiculous, right? You just basically take the first term and that's it. But that would be the sum of the first term. S sub 2, you would get A sub 1 plus A sub 2. S sub 3 would be A sub 1 plus A sub 2 plus A sub 3. So you keep doing this eventually, and they'll always want to know, like, what's the nth partial sum, right? So that means you're just going to add A sub 1 plus A sub 2 plus A sub 3 plus etc. all the way up to A sub n. Okay, so they can ask you to add up to however many partial terms or partial sums they want. Okay, but just know that the sub number, right, sub 1, sub 2, sub 3, sub 4, sub n, means that's how many terms you're going to be adding together. Okay, so we'll get to some of that stuff in a bit. Okay, so we talked about convergence and divergence. Okay, let's talk about a little bit how we can tell if something is convergent or divergent. So let's see. Here's example number 1. So are these convergent or divergent? So are these convergent or divergent? So here's the first one. The sum as n goes from 1 to infinity of 1 over 2 to the n. So the way you do this is you check the partial sums, okay? You got to figure out what are some of the partial sums. You want to find s sub 1, s sub 2, s sub 3, etc. Okay, so let's do that. Let's find a couple of the partial sums. So s sub 1 would be half. S sub 2 would be a sub 1, which is half, plus a sub 2, which is 1/4. Okay, so I'm just plugging in a 1, and then I'm plugging in a 2 into the n value. So 1 over 2 to the first, plus 1 over 2 to the second. So if I add this stuff up together, I get 3 over 4. Okay, now we're going to focus on these numbers right now. Let me give you one more partial sum. S sub 3 is half plus 1/4. We already know those answers. Plus, well, now I got to plug in a 3, so 1 over 2 to the third, that's 1 over 8. Okay, and that comes out to 7/8. Okay, so notice that the sequence, let me put right here, note that the sequence, let me highlight 7/8 here, the sequence of terms is half, 3/4, 7/8. So if I want to represent this as the nth partial sum, how do I write that? So I got a 1/2, a 3/4, a 7/8. Well, I do notice that the top part are only odd numbers, right? So the top part are only odd numbers, but they are missing like a 5, right? We just kind of skipped the 5. So how can I write a 1, 3, and a 7 as a function? And the same goes for 2, 4, and an 8. Well, I know 2, 4, and 8. 2 to the nth minus 1 for what? The top or the bottom? For the top. That'd be correct. 2 to the nth minus 1. Okay?
Why is it 2 to the n instead of 2 times n?
Well, 2 times n, if you plug in a 2, a 1, sorry, you'd get a 1, right? If you plug in a 2, you get 4 minus 1, which is 3, so that's good. But if you plug in a 3, what do you get? You get the missing digit, right? So if you're one of those that maybe struggles with the powers, check this out. Okay, I always tell people, here's a little hint. If you ever want to see if it's an nth power, then add 1 to the number and subtract 1. So if I subtract 1, I get 0, 2, and 6, right? And that doesn't look like anything familiar to me. It doesn't really help me, 0, 2, and 6. But if I add 1 to it, I get 2, 4, 8. And that's 2 to the n, right? But it's 1 less than 2 to the n, right? So it's 2 to the n minus 1. Okay? The bottom, well, that fits perfectly. That's 2 to the n. Right? So if you ever have trouble with that looks like this, add and subtract 1 to it and put it like above and below it and see if anything like that makes sense. And if you're like, oh, that's like 3 to the n, well then, okay, what did you do? I added 1, so that means you got to subtract 1. So it'd be 3 to the nth minus 1. That's going to be my pattern. Okay, those are some of the hardest ones to do. just so you guys are aware, like those are the tough ones. So if you kind of do that, it might help. All right, so now that I have this, I'm checking for convergence, right? So I just want to make sure that this sum actually converges to a value. And then right now I'm going to give you guys the definition for it and how I know I should do this, okay? So let's find the limit as n approaches infinity of s sub n. Okay, in other words, what's the limit as n approaches infinity of 2 to the n minus 1 over 2 to the n? What do we get for that? Not 0. Because this, this right here grows at the same rate, right? It's just going to be a 1. Yeah, just a 1. Okay? So since that converges to an actual finite number, then the series converges. So since the limit as n approaches infinity of s sub n converges, then the series converges. Now notice I didn't tell you what value the series converges to. I just told you that it does. Okay? We're not so worried about what it's converging to. We're just worried about, is it getting to some point where it's converging? Okay, so just to go over this again, we started off with a series. We took partial sums of that series to figure out the sequence that series is going to make eventually. Okay? Now we get that sequence and we rewrite it as an nth term. Okay? And we figure out, well, if I keep adding all those terms, a sub 1, a sub 2, a sub 3, which was half, 3/4, 7/8, if I keep adding those over and over and over again, is it going to add up to some finite value? Or is it going to add up to something infinite? So the way we check it is we check to see the limit of that partial sum, the nth partial sum, right? So we take the limit of the nth partial sum and it shows up to be something finite. So since it's a finite value, that means that the series will also add up to some finite value. I don't know what it is, but it is a finite value, some number somewhere. Who cares what it is? But it's going to add up to a finite number. So that tells me that it will converge. Okay? Let's do another one. Then I'm going to give you guys the theorem for this. So part B, we're going to do the sum as n goes from 1 to infinity of 1 over n minus 1 over n plus 1. Now this is something we call a telescoping series, and we'll talk about that soon as well. It'll make some sense maybe as we start going over this. But here's the series. They want to know whether or not this converges. So we're going to do the same thing we did the last time. Let's find the first partial sum. So that's 1 over 1 minus 1 over 2. So that's equal to half. Okay, so here's my first term. Let's find s sub 2. So that's 1 over 1 minus 1 over half. Plus, notice, the thing I put in parentheses, that's my first term, right? 1 minus half. That was my first term. Okay, now if you're wondering why didn't I just write half, you'll see right now why I just kind of did it like this. So 1 over 1 plus minus 1 over 2, that's the first term. Now the second term will be 1 over 2 minus 1 over 3. Well, notice how the middle terms cancel out. Negative half, positive half. So it's just 1 minus a third. So that's 2/3. All right, so far so good. S sub 3, that's 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus, now the third term is 1 over 3 minus 1 over 4. Notice how the middle terms cancel out. It's just 1 minus a quarter. So that's 3/4. Okay, so they call it telescoping because the further out you go, it doesn't matter. It's just the front end and the back end that actually makes sense. The rest cancels itself out. Okay? So every once in a while there's a weird thing where like the first term actually gets canceled, but the second little term will survive. I mean, things like that. But that's kind of what happens. Things tend to just cancel themselves out. So the sequence is 1/2, 2/3, 3/4, etc., right? So what's the nth term? Yeah, n over n plus 1. Yeah, there you go. So the limit as n approaches infinity of s sub n would be the limit as n approaches infinity of n over n plus 1, which is equal to, what? It's just 1. Right? Same degree top and bottom, so your coefficients will be 1 over 1, so that's equal to 1. So since the limit of the partial sum as you approach infinity converges, then the series must converge. Or I guess I could put right here, since the limit as n approaches infinity of s sub n converges to 1, then the series sum as n goes from 1 to infinity of 1 over n minus 1 over n plus 1 converges. So before we define a telescoping series, again, this is called a telescoping series. Let me give you a definition of convergent or divergent series. Okay. So definition of convergent or divergent series. So it says for an infinite series, the sum of a sub n. Notice they don't actually get too particular with what the lower and upper bounds are, but just for that, the nth partial sum is given by s sub n equal to a sub 1 plus a sub 2 plus a sub 3 plus etc. up to a sub n. So they're just stating something obvious right now, okay? So if you have an infinite series and the nth partial sum is given by s sub n, okay? If the sequence of partial sums If the sequence of partial sums S sub n converges to S. Now, when they say S, they just mean a number, okay? To some sum, right? An SUM, a sum. So if it converges to a number, an actual value, then the series sum of A sub n converges. The limit S is called the sum of the series. So the sum of the series. Okay? And S is normally defined as A sub 1 plus A sub 2 plus A sub 3 plus etc. plus A sub n plus etc. Okay? S is just like the infinite sum. Okay? Now, if S sub n diverges, then the series diverges. So now you can see why I went through and did S sub 1, S sub 2, S sub 3, right? To figure out the nth partial sum. Because if I can get S sub n and figure out an equation for it and then take its limit, if that converges, then the series converges. If it diverges, the series diverges. Okay? So it's important that you guys take these infinite series, find the partial sums, at least 3 of them, and try to develop a pattern for them. And that's why we had homework on pattern recognition, because you got to be able to figure out what's the pattern for it, what's the equation for the sequence, okay? And once you have that, take its limit. If it comes up to some finite value, great, that means it converges, therefore the series converges. If it's an infinite value, well, in that case, the series will diverge as well. Okay, now I'm going to define a telescoping series for you guys as well. That's another definition for us to write down. So telescoping series, they look like this: B sub 1 minus B sub 2 plus B sub 2 minus B sub 3 plus B sub 3 minus B sub 4, etc. Now we're just going to the nth term in that series that I'm showing you. But notice all the middle terms are going to cancel out, right? Because B sub 2 plus minus B sub 2 plus B sub 2, that's gone. Minus B sub 3 plus B sub 3, that's gone. Eventually the B sub n, right before I wrote B sub n, there was a negative B sub n there. Okay? But that's gone too. So that means that S sub n must be what? What would that be defined as? Think about it. Everything cancels. So it would just be B sub 1 minus. Yeah. That's my S sub n. Okay. S sub n will converge if it approaches a finite value as n approaches infinity. If S sub n converges, then its sum is S equal to B sub 1 minus the limit as n approaches infinity of b sub n plus 1. So if you need to find the actual sum of the telescoping series, you take the first term that's not canceled, okay, b sub 1, the first term that's not canceled, and then you subtract the limit of the last term. So if we can, which I think we can, we got 15 minutes. We're going to do one more example, and then we'll be done, okay? And it's going to be kind of like the one that we just did. So example number 3. So find the sum of the series. And here's the series. They give us the sum as n goes from 1 to infinity of 2 over 4n squared minus 1. All right, so we're going to do our S sub 1 and our S sub 2 and our S sub 3. So S sub 1 would be 2 over 4 minus 1, so that's just going to be 2/3. Now S sub 2 will be 2/3 plus 2 over, I got to plug in a 2, so that's 4 times 2 squared minus 1. So 2/3 plus, that's 16th, that's 2/15, right? So that comes out to 4/15? No, 4/5 if you reduced it, 4/5. Again, looking at this, looking at that. Okay, the next one, well, we have S sub 1, that's 2/3 plus 2/15 plus, now I got to do the third one, right? So 2 over 4 times 3 squared minus 1. Remember, the 2/3 and the 2/15, that's the first and the second term, okay? And then the third term would be whatever, 2 over 4 times 3 squared minus 1. So 3 squared, that's 9. 9 times 4 is 36. Minus 1 is 35. So that's 2/35. So if I add that stuff all together and simplify, we get 6/7. So my sequence is 2/3, 4/5, 6/7, etc. So what's S sub n? Remember, I got to start with 1. All right, and bottom? Notice it's just 1 more than the top, right? Yeah, so yeah, it's just 2n plus 1. So let's take our, let me rewrite that here. Let's take the limit of this thing. Okay, so the limit of this, 2n over 2n plus 1, okay, which actually is S sub n, comes out to what? That's a 1. So that means since the limit as n approaches infinity of S sub n converges, then the sum as n goes from 1 to infinity of what was it? 2 over 4n squared minus 1 also converges. Now, as you guys are writing this down, the reason why I waited to do this example after I defined telescoping sums is because of the following. Okay, 2 over 4n squared minus 1 could actually be rewritten as 2n minus 1, 2n plus 1, which you could have said was the same as this. Yeah, and if you find out what A and B are, their values, by using partial sums, right? Yeah, the partial fractions, you could just do that and you'll notice things will start to cancel. Just so you know, this actually does turn out eventually. It comes out to 1 over 2n minus 1 minus 1 over 2n plus 1. That's what eventually happens to it. So then you'd be taking this, and then when you plug in a 1, you get a half minus a third, and then the next one will be a third minus a fifth, and then the next one is et cetera, et cetera, et cetera, right? So they start canceling out, canceling out, canceling out, and you will get the same type of sequence. So just to let you know, whenever you see something that you can factor out, maybe it's easier to break it apart and use partial fractions to kind of rewrite a telescoping sum. You'll notice you don't have to do it, okay? You don't have to do it. We just did it up there, and we were able to find our answer without having to turn it into a telescoping series. But you could if you want to, okay? So we'll stop there. Tomorrow we'll jump into geometric sequences and whether they're convergent or divergent. That one's pretty easy to test. And then we'll get into the nth term test for divergence maybe as well. If not, we'll save that for Thursday. Okay? So go ahead and relax for now. I don't know if I'm giving you guys homework for this, so let me check, okay? For at least the first little piece of it.
Here's the assignments from your wife.
Okay, thank you. So 605. I think I waited till everything was done, so we'll just wait.